And thank you all for showing up for this event. Yes, Steve was a great physicist, but what really deeply marks him was his tenacity in trying to understand what the world is like and how to incorporate that into a meaningful theory of the nature of our world. He focused largely on the small scale part of it. That's elementary particle physics. He also was fascinated by the large scale part, which is my lecture today. To begin, I think it helps to imagine stepping back and looking at the world at large by getting the bigger picture. I start with this image of planet Earth, which is of historic interest because it is the first released to the general public that is taken far enough away that you can see that it is an island of matter surrounded by vast areas of close to dead, empty space. It prompted the knowledge that a phrase we didn't have then, sustainability, but the notion we should find a way to live in a sustainable way on our very limited planet. It inspired, as an illustration, this book, The Whole Earth Catalog. That's the same photograph of Earth. This is a catalog an inch thick of tools for living, all kinds of tools. If you're into this sort of thing, you'll love flipping through the pages. Here, for example, you want to build a wood frame home. Here's how to start. The next planet out, Mars. See that enormous valley carved into it? Ideas, of course, about what it's like, how it got that way, but no firm theory yet. Here's another image of Mars. It looks just like the braided streams in the delta of a river as it reaches the ocean or a lake. It looks as though there was water on Mars. Fascinating. It left traces. Did it leave life? Well, so far not found. Here, further out, the next planet, Jupiter. Jupiter has about the composition of the sun. It's not radiating like the sun because its pressure at the center is not high enough, but it is still cooling from the heat of formation. Packets of gas warm gas are rising, losing energy as radiation, cooling, while moving down again. This motion up and down, together with rotation, produced this fascinating pattern of structures across the planet. Here is an image of the sun, and I draw your attention in particular to the small-scale photograph on the right, showing the bubbly nature of the surface of the sun. Maybe you've seen the same pattern as you stood staring at a cooking soup if it's particularly thick. Same effect here. Plasma is rising, cooling, sinking, and making that structure. The sun is not alone, of course. Here's a map of the nearby stars. The sizes of the stars are enormously exaggerated relative to the distance between stars, but the relative sizes are realistic and the colors are realistic too. The most massive star nearby is Sirius A at about twice the mass of the sun. That greater mass produces a greater central dense pressure that produces a lot more rapid rate of reaction of the nuclear reactions that convert hydrogen to helium and release energy that rises up to the surface and is radiated away. That rate of reaction is much faster in Sirius. It makes the surface much hotter, and it means that it is going to run out of nuclear fuel sooner than the sun. Besides Sirius A, you may see Sirius B as that little dot. That began as a star even more massive than Sirius A. It burned its fuel even more prodigiously. It eventually ran out of fuel, expelled much of the mass in a wind, and left the rest of the mass as a white dwarf. That will happen to Sirius well before anything disturbing happens to the sun. You'll notice that there are a couple of other stars bigger than the sun, and a lot of stars that are smaller. They're those red things. Their pressure toward the center is small enough that they're converting hydrogen to helium very slowly. They're going to last a lot longer. They're radiating much more slowly. There is, toward the end of this map, and shown here in a little more detail, the triple star system, Proxima Centauri. That little red dot is a star, barely radiating. It has at least 2 planets around them. One of those planets is just at the right distance from that star, so that water on the surface of that planet, if there is any, would neither boil away nor freeze. That's a very generous definition of a habitable zone, but still, wouldn't you love to see what is on the surface of that planet? And it's only 4 light years or so away. It's just conceivable that you could get there. Getting back would be another challenge entirely. There is, of course, talk of sending drones to look at what's on the surface. We are in a galaxy of stars. It's flattened, supported by rotation. Hard to see because we're in it, so we'll take another step back and look at a nearby galaxy the nearby galaxy that looks a lot like our galaxy of stars, the Milky Way. It is, to me, an image of great beauty, just as an image. And it is, to me, also a fascinating illustration of science. Can you see the dark lanes? They're caused by dust. A candle may make smoke. Massive stars can do the same. That smoke or dust accumulates in these lanes and makes the dark patterns. You see blue patches. That's where stars have formed fairly recently. Among young stars, there are the massive ones that are blue and hot, and that's what makes the blue light. You see other patches of red. That's where the young stars have been so bright that they've ionized the interstellar gas, mostly hydrogen. Where that gas has been ionized, it tends to recombine to neutral atomic hydrogen. That emits a strong line in the red. And where you see red, that's where plasma has been recombining. You also see, most clearly toward the center, but throughout, a yellow haze. That's the light of some 1,000 million stars similar to the sun. Now, astronomers have established that, at least in our neighborhood, there are at least as many planets as there are stars. It's a good bet, therefore, that in this galaxy, there are some 1,000 million stars with planets on which all kinds of things, marvelous things are happening that we, the human race, will never see. It's worth pondering. Here is a map of the distribution of nearby galaxies. This is two orthogonal views, one view looking this way and another view looking this way. So, for example, this little black dot on the top with the arrow pointing to it is over there, seen from the other direction. You notice a flat distribution. The red dots are stars as massive roughly as the sun, galaxies as massive as the Milky Way. The black dots, smaller little items. Here are some examples of images of these galaxies, spirals mostly, the occasional elliptical galaxy. That's a clumpy distribution. And you notice this charming little dwarf here with a cloud of atomic hydrogen around it, sitting in splendid isolation in that vast empty region. So what's it doing there? There are ideas, but this is young science. I don't think we have a good, clear understanding of why these things happen. Here is what you see if you step back still further. What you see is the texture of the distribution of matter in the universe on large scales. Notice in the middle, that clump of galaxies, that is in effect a galaxy of galaxies, an immense concentration. Look to the left, look to the right, you see something similar. You see something here that is quite remarkable, rather like the dog that did not bark in the night. You step back further and you did not see anything new apart from that great cluster of galaxies. That's new, and that's important. We've been so used to discovering layer upon layer, and of course there are layer upon layers going down in scale too, but yet we run out of structure. Deeper samples taken since then have confirmed this, that on large scales, the universe is quite close to uniform. That has a big impact on what we can do. If the universe is close to uniform, then you don't have to make a theory of what happens to each individual part. They're all much the same on large scales. And we can then talk about the evolution of the mean distribution of matter in the universe and evolution in the way it changes. Oh, I just thought, science is done by people. This catalog was obtained by Donald Shane, the serious one here, a little embarrassed, a great astronomer, truly brave. People talk about bravery. This guy spent 10 years of his life scanning photographs of the sky to pick out all of the galaxies, the brightest 1 million. 1 million is a very big number. It took him 10 years. He, working with his assistant, Carl Wertman, at the Lick Observatory in California. California. These are graduate students, Jim Fry, Ray Siniera, Mike Seldner, and others off scale, who rallied round to analyze that data. Here's an example of it. These are copies of the data sheets from Donald Shane and Carl Wertman, and that's computer printout. You talk about bravery. This is real bravery, a devotion to science so tight that he, like Weinberg, would go to great lengths to get this data. And the charming part is that when Donald Shane completed this data in the 1950s, there was no way you could handle it. What do you do with 1 million numbers? Nowadays, it's trivial. You have high-speed computers. We have had a computer capable of at last analyzing these data. And I had the great pleasure of taking this image to Donald Shane and asking him, so is this what you saw? And he laughed and said, I was looking at this one galaxy at a time. All right, this is a deeply important result, but let's push on. Albert Einstein was another great physicist, also indefatigable in his attempt to get at the best theory, including his general relativity, though he had no right at all to invent that theory because there was no way to test it for another half century after he invented it. But his instinct was right. He developed a theory that now is widely applied. Maybe you've heard about gravitational wave detection. That's general relativity. The expanding universe and the tests of it, that's general relativity. Laboratory experiments, general relativity, all passed. He also concocted the idea that a logically simple universe would be uniform, the same everywhere. Again, he had absolutely no right to think that. No right at all. In fact, the astronomer beside him, who was looking skeptical, Willem de Sitter, director of astronomy at the Leiden Observatory, was rather cross with Einstein, saying, you have no right to make this assumption because we know the galaxies are clumpy in their distribution. You saw the clumps. But Einstein persevered, And somehow, well, sometimes geniuses are right. Sometimes they're wrong. And I'm going to give you an example, but this case, he was right. He couldn't see that, but he saw it somehow. A uniform universe. Now, this is kind of interesting. Let us look at a consequence. Let us imagine that we lived in only two dimensions, two spatial dimensions, not three. You live on the surface of this balloon. You must not ask what is above or below the surface. You don't live there. You live on the surface. The universe is uniform on average, and the surface of the balloon is uniform on average. The galaxies are uniformly distributed. Now, again, as indicated here, oh, and I might mention that this is Professor Dr. Willem de Sitter. It's from an essay he wrote in a local newspaper. That figure is lambda, except backwards, the Greek letter lambda. The Greek letter lambda forwards and in capital is what we call Einstein's cosmological constant, which I will get to. Anyway, now imagine that the balloon is blowing up. And again, be very careful. We are not expanding. You and I may be, but that's only the result of perhaps overconsumption of food. The galaxy is not expanding, except perhaps for accretion, gravitational accretion of matter drifting into it. But it is the galaxies moving apart. And you notice something neat. If I had a pointer, I would point. Well, my arms are fairly long. So imagine you're on a galaxy. You look around and you see all the other galaxies are moving away from you. You say, wow, the universe is expanding, and it's expanding from me. Except you notice everybody has the same impression. This galaxy sees these guys moving away from, this guy sees these people moving away. This predicts that the rate of recession of a galaxy from me is proportional to the distance. Here is Edwin Hubble. Actually, I should introduce the actors here first. It's kind of interesting to see the actors who are making these great contributions. Percival Lowell was a member of the Lowell family of Boston. They were the creme de la creme, the highest levels. Well, all right, there is a poem. So now we are in Boston, the home of the bean and the cod, where the Lowells talk only to asters, and the asters speak only to God. Lowell got fascinated by the idea that there might be a civilization on Mars, and it's making canals. That was a big canal building time. His memory is celebrated by astronomers because he chose to build his observatory from his private fortune in a place that's good for astronomy, Flagstaff, Arizona, not a place where it was convenient to get to. He was also celebrated for hiring excellent people to instrument his telescope and use it. That includes Melvin Slipher, who was able to establish that the galaxies are moving away from us. He used the Doppler effect. You're familiar with it. You stand by the side of the road and you hear the cars. That's not a change of tone. Rather, as the car is rushing toward you, the sound waves are compressed, raises the frequency. As the car rushes back away from you, it stretches the sound waves, lowers their frequency. Same with light. And by observing that effect, Slipher was able to deduce that the galaxies are moving away from us. As if the world were expanding, the universe were expanding. Henrietta Leavitt at the Harvard College Observatory was what in those days were known as computers, which was a laborious job in those days. But she was a very intelligent person. She showed astronomers how to measure distances to galaxies. Hubble in California used Slipher's motions away, Leavitt's distances to establish that the further the galaxy, the greater the recession velocity, the pattern you expect from that balloon analogy. And here are results. His publication paper, 1929, is a little embarrassing. And would you buy a demonstration that that's a linear relation? Well, maybe. But by 1936, when I was 1 year old, they had reached recession velocities of 10% of the speed of light. Truly remarkable. And it's a nice linear line. Interesting, from 36, it took another, well, more than half a century to get that next factor of 10 down below. So here's one piece of evidence that the universe is expanding. You, of course, need more than one piece of evidence to be at all convinced of that. So we turn to a piece of evidence. Thermal radiation. You've all, I'm sure, sat by the campfire and felt the warmth of the thermal radiation from the coals. If you have real thermal equilibrium by, say, putting a container around the radiation and allowing it to relax to statistical equilibrium, then you find that the intensity at each frequency is a well-predicted thing. Examples here. The evidence now is very clear. Our universe is filled with a sea of radiation at about 3 degrees Kelvin. This is 300, so if you go down a factor of 100, you'll find a bump in here at microwave wavelengths, about that of your microwave oven. It is filling our universe with thermal radiation. Again, I take the liberty of showing a few slides of people involved in this. Here is Ray Weiss, who is the leader in the development of the technology that led to the observation of gravitational waves from merging massive objects. A great physicist. The building was thrown up during World War II for war research, radar, deeply essential. Here's a photograph of people on top of that temporary building, torn down only recently. I guess it was a fire hazard. It's all wood. A shame to lose that historic building, but it was, well, like, what can you do? Bob Dickey on the far right. That device he invented, a microwave radiometer, is able to pick up these microwaves and measure them precisely. Intensity at each wavelength, each frequency. Just to show you that it could do that, and to show us, Bob set up an experiment in which he scanned the sky of Cambridge from the top of that building. There were chimneys that are hot. Now here, you notice that the temperature is increasing, going downward, 100, 150, 200, 300 degrees. The number here is the angle from the zenith. So the big numbers are he's nearly near the equator, near the horizon. And you notice that the trace goes down, it senses high temperature here and here. Two of those buildings have warm chimneys. It's a really remarkably sensitive development. And Bob Dickey, always a very inventive physicist, curious, like Weinberg, to keep curiosity. He went down to Florida for the purpose of studying the transmission of microwave radiation, which is affected by humidity. So he went to the most humid spot he could find in the Americas, in the center of Florida, and made measurements, including the demonstration that there's very little radiation from cosmic matter. He put a bound of 20 degrees. If he had taken that instrument back to Cambridge, put it on the roof in a cold winter day when the humidity is very low, he would have put a much closer limit and closer to 3 degrees. But, well, didn't know that that would be an interesting thing to do. Instead, in about 1964, Bob Dickey assembled David Wilkinson on the left, me and Peter Roll, three of his young postdocs in his research group, and said, I think there's a good chance that the universe began hot and it's filled with a sea of thermal radiation, and it ought to be still there. He said to Peter Roll and David Wilkinson, why don't you build a radiometer to look for this radiation? He didn't say, but it was true, that that radiometer was invented by him during the Second World War. He turned casually to see me and remarked, why don't you think about the theoretical implications? Peter Roll went off into education. David Wilkinson and I spent the rest of our careers studying, following Bob's suggestion. Brilliant people can sometimes make uncannily prescient remarks. What do we have next? We have David Wilkinson. You see him holding the screwdriver. And Peter Roll, you can make out the plaid shirt, a Dickey radiometer. They were looking for this radiation. Meanwhile, not far from Princeton, at Bell Telephone Laboratories, there were experiments going on for the purpose of communication by microwaves. This gave us what is to me the abomination of students walking through campuses, staring at their cell phones, instead of these beautiful buildings, trees. What? You can't stop progress. This looks like a pretty rough setup. You notice the rough timber holding up this horn reflector. But inside that cabin was some very sophisticated electronics that people understood very well. And so were able to both measure the rate at which they were receiving microwave radiation at a given wavelength and the contributions to what they were receiving by all known sources within the instrument. And they were forced to postulate that about 2 degrees worth of energy is coming from the back lobes that diffract around to get into the horn. The engineers knew perfectly well that that's absurd. These horn reflectors were very well designed to eliminate backlobe radiation, radiation coming in from the back. That was purely made up to balance the books. It remained a dirty little secret at Bell Telephone Laboratories for the next 5 years that whenever they built one of these receivers, they got this annoying little bit of extra radiation. Where in the world is it coming from? This is crazy. You got to do something. 2 young people who had joined Bell Telephone Laboratories just resolved that they would get at the source of this radiation. They spent a lot of time looking at all possible sources of this extra 2 or 3 degrees. They are to be deeply credited for refusing to give up. And we also have to mention their supervisor somehow was willing to allow them to spend the time required to look at all these possibilities. That is because Bell Telephone Laboratories had a monopoly on telephones, and they were making an enormous amount of money, so they could support really high-class research in the Bell Labs research stations. Anyway, these two, Bob Wilson and Arnold Penzias, were also to be credited deeply for complaining. Why can't we understand the source of this radiation? Until the last word got back to the experiment at Princeton, who were looking for this. So good. It happened then that the connection was made in early 1965. Here was the situation in summer 65. You have intensity going up, wavelengths going to the right. Here is what you're expecting to see, this line. Here is a notion that there are sources of radiation from galaxies. Here are their values as they fill space. This is the amount of radiation that fills space on average because of the radiation from galaxies. Here's radiation from dust in our galaxy and others. Here's their point. Now, I showed this slide at a meeting of the American Philosophical Society in New York. And I have to report that, well, to be colloquial, a titter ran through the audience. You're making quite a claim, young man. 1 point? And you've got a great discovery? Well, of course not. My feeling in those days was simple. There was no guarantee that David Wilkinson and Peter Roll would find anything. I was instructed to look at the implications, so I had a backup theory. What if it's a cold universe? But I had a backup theory for a hot universe too. And there was an exciting possibility that that might be what's happening here. Soon we had a second point, the Princeton group. And there are 2 points, and at least they follow the curve. There then followed a period of great distress to me, emotional, because time and again, as people tried to measure the intensity going over the peak, they found an anomaly, excess radiation. Berkeley and Nagoya was the most beautiful of these experiments. You see the data points 1, 2, 3, 4. They're not quite fitting a thermal curve. It is easy to imagine why this would be. If in the early universe there were massive explosions, maybe gravitational collapses to black holes, it would release energy that would add to the short wavelength part of this spectrum. If that were the case, and then it would be horrible because it would mess up the distribution of the radiation across the sky. And that would mean we have no trace of the way it was originally distributed. A horrible thought. So at last, well, people managed to make the measurements by going into space. There were 2 groups making the measurements. Interesting coincidence. It took each group roughly 15 years from start to finish. They finished within a few months of each other. Either result would be gorgeous. It is gorgeous. It is a close to exactly thermal spectrum. It is a pretty clear signature of the remnants of an early universe that was hot, relaxed to thermal equilibrium. The expansion of the universe cools the radiation. Either one of these is worth a Nobel Prize. I'm seriously upset with the Nobel Committee for not recognizing that point. So John Mather got the Nobel Prize for the curve above. Herb Gush didn't. Well, the one problem is Herb is Canadian, and we tend to be diffidents. So he was very easy with it. All right, we've got to learn to complain more. Okay, so this is again a piece of evidence that the universe has expanded from a hot, dense state. Now, in the early 80s, in 1980, there was a problem, very difficult to understand. The distribution of galaxies is clumpy. The universe is the same on very large scales, but on the scales illustrated here, it's really bumpy. On similar scales, the temperature of the radiation does vary across the sky, but by parts in 100,000. A vast, really vast difference. How did the radiation keep so smooth when the radiant matter grew so clumpy? That was, in 1980, a growing crisis. What in the world is going on? The solution, dark matter, had some origins with Steve Weinberg. People in elementary particles were fascinated at this time with discovering new particles. They were finding lots of them. They were fleshing out the standard theory for elementary particle physics. And for a time in the 1970s, people were fascinated with the notion that there might be kinds of matter that don't interact with ordinary, as we say, baryonic matter. A partial list. Curious that also the notion a candidate for what we now call dark matter was found in 5 papers by different authors, independent. One often talks about a multiplicity of discoveries. A common phrase that I know historians detest, the idea was in the air, but it's a good description. Physicists talk to each other. They exchange ideas. They even exchange ideas, but not by what they don't say, as well as what they say. These ideas filter around like gossip. And the idea that there might be a particle that doesn't interact with ordinary matter as part of the standard model was realized in 5 independent papers. Pete Hutt was the first. He's now at the Princeton Institute for Advanced Study. He told me that he received a nice handwritten letter from Steve Weinberg, who was the second with Ben Lee to make this proposal. I pressed Pete Hutt, find that letter. Got to show it to Steve, because Steve forgot he wrote it. And he thought he was the first, but he could never find it. Too bad. Then others. And the illustration of the fact that although physicists tend to be sort of secretive, I don't know, hermits, but no, they communicate. They really do. So we had this notion of dark matter. And of course, the notion of dark matter is just what we needed. Because when the galaxies are growing, they're pulling material together. That material drags radiation because it's ionized. But if there is non-baryonic matter, dark matter, of the sort that these particle physicists were considering, it wouldn't be dragged, and so it could get clumpy without dragging the radiation. So the problem is solved, and a measure of this is a measure of the large scale anisotropy distribution across the sky of the radiation I predicted was this. This is in 1970, and this number came, well, about a half a century later. It was right within the uncertainty, the same number. Isn't that curious? But now it's important to notice a big difference. I wish now to show you a demonstration of great sophistication, which I have here. So as a child, I thought it was very cute. It always comes out the same, and I'm always pleased. This boundary condition sets the wavelength that you're hearing. This is a shorter wavelength, the higher frequency. I'll delight you by playing it again. Isn't that neat? That's an illustration of the important role in physics of boundary conditions. Here's another illustration. Here I have a plastic plate with a little water in it. I'm standing above it with my cell phone. I tap the plate just a bit and snapped a photograph. Do you see how the pattern follows the boundary? There is a very similar evolution in the distribution as the growth of matter in the evolution of the distribution of matter in an expanding universe. Here is Bob Dickey again. Here is David Wilkinson on the right, and in between Jerry Yu, my first graduate student. Jerry Yu and I worked on a theory for how this would go, in terms that best I can do. Imagine decomposing the distribution of matter into plane waves. A plane wave is just a wave going in one direction, up and down. And of course, the matter in the early universe is hot, so it's ionized. So you have a mixture of electrons, ions, and radiation. The radiation scatters the electrons scatter the ions. The result is a fluid with a high pressure and some viscosity. That fluid, if the universe is all inhomogeneous, will oscillate. And the oscillation will mean that the amplitude goes up and down until the temperature of the universe drops to 3,000 degrees when it was 1,000th its present size measured linearly. Then the electrons combine with the ions, the radiation moves off freely, and the matter can start to grow more clumpy by the pull of gravity. You notice that at this particular wavelength, the amplitude starts to grow in the same direction as the beginning. Change the wavelength a little bit, and this will come up going down. In between, there will be an unlucky mode in which the amplitude is just zero. That causes this pattern. A little complicated, but you get the basic idea. You get zeros in this so-called power spectrum of the galaxy distribution. What was measured, that's 1970. That's 47 years later, this beautiful measurement. You notice one whopping difference. These have zeros, these don't. Instead, these are very little oscillations. Why is that? Of course, the answer is simple. We didn't think of dark matter. The fact that these oscillations have such modest size is directly understood by the postulate we had already made of dark matter. It's these sort of nice, unanticipated coincidences that gives us a lot of confidence that we're on the right trail, which is good. Here, modern situation, beautiful measurements. We don't get any details. This is the radiation above. This is the matter distribution below, measured by galaxies. The basic thing first, the solid line is the theory, and the dots are the measurements. Wow. Second, and I think really deeply moving, this theory is the same for this line for the matter distribution and this line for the radiation angular distribution. These two results are measured in wildly different ways. And the effect of what's happening at wildly different times, and they're consistent. Wow, that is really good. Makes you feel sure that things are going well. To illustrate another aspect of this, you had to choose parameters. For example, you had to know the mass density in ordinary matter. That's important because in the very early universe, the theory says that some of that matter is going to end up as helium. So coming out of the very early universe will be a universe with hydrogen, helium about a third the mass of the total, and then trace elements of slightly higher, heavier isotopes. That helium production can be compared to the helium in old stars. And we get about the right consistency if the baryon density in units that needn't bother us is here. That pattern you saw, the theory requires a value of the baryon density. It's here, quite similar. And of course, you can measure the baryon density nearby, and the measurements are a little better than that now. But it's about the same. You notice that this is really something very, very impressive. The helium is being formed when the universe was 10 to the 9th, 1,000 million times hotter than it is now. When the universe was really, really hot and dense. The evolution since then required, from those wiggles you saw, another baryon, gave an independent way of measuring the baryon density. You have another independent way from what's happening locally, and they agree to pretty good accuracy. The same with these other parameters. Hubble's constant, for example. Now, it is deeply impressive to me that the Hubble constant you infer from what was happening when the universe was 1,000 times smaller than now agrees within 10% of the Hubble constant you measure locally. That's really impressive. Really impressive, despite the fact that the two disagree by 10%. That's a famous anomaly. Although, of course, I'm going to say some positive things about that anomaly, that it is impressive that you got so close. It really tells me that we surely are on the right track. But on the other hand, before I get into anomalies, I just can't resist pointing out that the mass density in all kinds of matter is small. In the 1990s, everyone knew that this number should be unity, and it's clearly not. It was a real crisis. In 1984, I said, we are going to have to bite the bullet and accept the idea of Einstein's cosmological constant. Notorious is the fact that Einstein disliked that constant. Here is the Abbé Georges Lemaitre with the caller Einstein. Lemaitre in 1930 understood general relativity better than Einstein. And he saw the advantage of keeping Einstein's cosmological constant. Following World War II, he wrote to Einstein, trying to persuade Einstein to think more favorably about this cosmological constant. Here you see, I'll read it. Dear Professor Lemaitre, I thank you very much for your kind letter, et cetera, et cetera, et cetera. Since I've introduced this term, I had always a bad conscience. And down here, I cannot help to feel it strongly, and I'm unable to believe that such an ugly thing should be realized in nature. That's Einstein's cosmological constant, and the low mass density in this table drove me to put it back. I remember a young theorist saying to me, "You're only doing this to annoy." And I'm delighted because you may know the Lewis Carroll poems. When you're a baby, be stern with your baby when it sneezes. You know it does it only because it teases. And so I've always thought that my young friend I should have responded, but I do it because it really teases, and it did. People just didn't like that notion, but we had to learn to live with it. An example of the fact, no matter how great your intuition, you're going to be wrong sometimes. I go on to another topic. Here are Gérard de Vaucouleurs and Antoinette de Vaucouleurs, Paris, 1962. I hope it's April. An elegant couple. They came here. I've been at the University of Texas in Austin for quite a while. Well, here they produced this volume. You can see Gérard de Vaucouleurs, Antoinette de Vaucouleurs, reference catalog of bright galaxies. I spent hours poring over that catalog to use it to get mass density estimates. I remind you that there are these great galaxies of galaxies, like that thing in the middle of the picture. And de Vaucouleurs noticed that that we are in a galaxy, and there are other galaxies around and about. They seem to be lying in a plane, which he called the locus supercluster. He introduced this idea in the 50s, if not earlier, and people laughed. People could not think there'd be such a silly thing as a plane of galaxies. But he was right. And in the 80s and 90s, people started recognizing that the clusters of galaxies tend to be on the same plane, extending far out. This is a photograph, a map I made illustrating it, which of course, if I were more mature, I would have done a much clearer image. But anyway, this curved line is the direction in the sky that is along this de Vaucouleurs locus supercluster plane. And where do you find the rich groups and clusters? All close to the plane. Isn't that a remarkable thing? Why is that? it's the community, by and large, who study how galaxies form, don't know this. And it's an inconvenient little discovery. How in the world do you understand why this is? It means it's an example of why we can say with great certainty first that the notion of the hot Big Bang, expansion of the universe from a hot dense state, has good empirical support, and at the same time, it's an incomplete theory because it can't account for this. The same is true, you understand, of every one of our laws of physics. They're wonderfully accurate, some of them, but they're all incomplete. You ask an awkward question, the theory can't answer it. That's just the way it is. And that's why we have departments of physics who struggle to improve the evidence for all these theories. I never keep track of time. I could ramble on for hours. How much have I spent? An hour. All right, very quickly, very quickly. Here is an illustration of the growth of matter distribution in the standard theory. This is only dark matter. The baryons have been put aside. The yellow dots are going to end up merged in the center of this image. That is to say, the theory predicts the structure grows by merging of clumps that form clumps of clumps that form clumps of clumps of clumps, and so on. And hierarchical growth illustrated here. Time is going down, little clumps form bigger clumps to form bigger clumps to form bigger clumps. This is the merger tree concept. I have checked that that phrase, merger tree, appears in the literature of astronomy in 327 papers in 2022, 268 in 2021, and so on. It's a wildly popular idea, but it's manifestly wrong. I'll show you why I say that. Well, here are examples. It happens often. But on the right, what do you see? You see well, no, you don't see it. Where am I? Oh, yeah, I got a little ahead of myself. Now you see it. Here's a galaxy. A galaxy like the Milky Way happens to be seen edge on. And isn't it remarkably, wonderfully flat? Here's another. You see it slightly tilted. But look across the face of this galaxy, nothing interesting at the center. It's wonderfully flat. This is not what would happen if you formed these galaxies by merging, and if there were stars forming in all of the subhalos that are merging to form the big halo. Because if you have two subhalos that are going to merge, if each has a little disk forming in it, when you slam those two together, those two stars in the disk are not going to remain in the disk. They'll be flung about. So they end up in a stellar halo. These galaxies have stellar halos, but they have very modest amounts of stars. To understand this, you have to postulate either that the galaxy didn't form stars until merging was close to complete, which is hard to understand why that would be. And furthermore, it contradicts the evidence that galaxies form pretty early, or else that there was not this merging. Isn't that a remarkable effect? Again, I say, this doesn't mean that the notion of the universe expanding from a hot, dense state is wrong. It only means that the notion as we have it now is approximate, incomplete, and will require improvements. I'm happy to leave the generations to come the improvements to be discovered. So thank you very much.
Good afternoon. My name is Jay Hartzell. I'm the president here at UT Austin. Thank you, Dr. Peebles, for your kind words and your insights and perspectives. Your presentation was not only insightful, but also provided a fitting tribute to the work and the legacy of Dr. Stephen Weinberg. Dr. Weinberg was one of the most celebrated scientists of his time and one of the greatest faculty members in the proud history of our university. He transformed our knowledge of the universe. He was prolific in his writings and his research, and he connected the world of science with other disciplines such as arts and culture. Dr. Weinberg also appreciated the role of science and scientists in making the world a better place, such as when he used his considerable credibility to influence leaders on issues such as nuclear nonproliferation. Not everyone is going to win a Nobel Prize or a National Medal of Science like Dr. Weinberg, but we can all make an impact. This is the example that Dr. Weinberg set. He applied his brilliance and his research to make a positive impact on the world and on our students. Part of what makes the university special is our talent. And while we're fortunate to have outstanding talent across the 40 acres, Stephen Weinberg was the type of scholar who makes a real difference, someone who is a magnet for other highly talented individuals and who sets the right cultural and intellectual tone on campus. Today, we've been fortunate to hear from someone who, even in the great pantheon of Princeton, fulfills that same role. That's why I want to again thank Dr. Peebles for being here to share his insights with us. And Dr. Peebles, this is why I'm honored on behalf of the University of Texas at Austin to present you with the Stephen Weinberg Memorial Lecture Medal. Congratulations.
Well, thank you. Not so I'll only say, Steve was a great, I always enjoyed the conversation with him, but he had strong opinions. And I do too. That's part of the game.
It's good to have an honoree who's used to receiving medals. So thank you. We're going to transition to some questions for Dr. Peebles, which Carolyn Dockery will moderate. Our staff will have microphones around the room. And if you're watching virtually, you can ask questions through the chat function in Zoom. And now I'm going to hand back over to Katie.
Actually, I'm going to moderate,
Oh.
and Carolyn is going to carry the mic around the room. So
Okay.
we're ready to take some questions from the audience.
Congratulations, Dr. Peebles. I have a question concerning a speed of light. What do you think about a variable speed of light in the early universe, and then the theory and a slower speed of light in the later universe?
Right. Of course, that idea has been discussed. There are constraints. If you change the speed of light and leave everything else the same, you are going to affect, for example, the predictions I showed in all those oscillations, because the speed of light is one of the parameters that affects just that shape. So there are tight constraints. Of course, you could ask more generally, the strength of the electromagnetic interaction could change with time, but it certainly doesn't seem to be. The strength of gravitational interaction is remarkably small. It leads to the notion that maybe it's small because it's been decaying, but yet the evidence is that it's stationary, it's static. Early universe physics is tightly constrained, but still there are very interesting possibilities about how physics back then, at very early time, could be in one way or another different from what we established in the laboratory now.
Thank you, Dr. Peebles, for the great talk. I was wondering, I know that many theorists posit a dark matter particle, right? What sort of evidence would actually conclude that such a particle actually exists if it doesn't interact with light or anything?
Right. To me, the evidence already exists. It is the success of the theory that depends on that dark matter. To the extent that that theory is successful, it is the evidence we seek of its existence. As time goes on, those measurements will improve, and we can hope for ever tighter evidence. We have no guarantee that the dark matter will ever be detected in the laboratory. It is worth pausing to reflect. We had no guarantee that physics would work. Why should we imagine that the world is comprehensible in its fundamental behavior? But it was, well, without thinking about it, I think people just assumed it could work and made great progress. And I don't want to make people uneasy by saying, well, no, well, maybe we'll never detect the dark matter. But there it is, it's a possibility. The lack of and you know, people have been looking for detection of that dark matter for 40 years, since the early 1980s. And now, 40 years. They started almost immediately after I proposed it. Does that mean that the dark matter exists? Absolutely not. It only means that it's very hard to detect. And if we have the indirect evidence, which is certainly in abundance now, I think I feel comfortable with the fact that it may not ever be detectable. But I don't want to discourage people from looking. And I always live in the hope that one day I'll open up the newspaper. I can't stand seeing it on the web, or it's got to be paper before me, and there'll be a screaming headlines. It's been discovered, it's been detected. But maybe that'll never happen.
Well, Jim, I'm one of the people who hopes that we are going to detect the dark matter.
Well,
particle. You know, I've been working on it, so.
oh, yes. I would be delighted if you, I would be delighted if you succeeded. But if you didn't succeed, I'd feel very sorry. But that's the breaks, my friend.
Dr. Freese, we have a question online from a student.
Ah.
What advice would you give young undergraduate physicists who would like to start doing research in dark matter and related areas in cosmology?
Well, of course, there are really two traditional lines of research. One is to improve evidence you have, make it better. The other is to look for something new. The payoff for something new is much higher than an advance in what we already know, improve it. But of course, the probability of payment is not large. And so you do well first to consider, keep your mind open to new ideas, but second, to be a little bit cautious about following them too far, or you may be wasting a lot of time. I don't know how you draw the balance between the two, and it will be partly your taste. How speculative do you want to be? I would warn a young student, don't spend all your time thinking about unknown ideas, speculative ideas. Spend some of your time establishing a reputation as someone who can do good work in fields that are well established and must be improved. But over the weekend, yes, be adventurous. Think outside the box, as one says. We have many unanswered questions. I mentioned a few of them. There are many more. Some of those questions are going to end up being meaningless. It'll be some obvious explanation. Others will be pointing to a problem with lambda CDM that will be solved when we have enough clues in a better theory. My bet is the theory will have something that acts like dark matter and acts like something like Einstein's cosmological constant, but it'll be better because it'll fit more data more accurately. That will happen. It's happened time and time again. I bet it'll happen again. And you could be part of that.
Yeah, we need another Einstein to figure out what this pie picture of the universe is. We really do. This is very strange.
Yes,
What a
yes.
horrible idea, Jim.
Yes. Oh, yeah.
No, thank you.
I know. And you know, it's been on the books a long time.
Yeah.
In the 1930s, people understood a real problem that the vacuum energy density of quantum physics is absurdly large. That means an absurdly large lambda.
Off by 10 to the 122 in the exponent.
Yeah, something like that.
Yeah.
Yeah.
Weinberg called this one of the great unsolved problems of physics. if
Oh,
not
it is.
perhaps he even said it was the unsolved problem. Yeah.
Well,
So yeah, we need help with from.
We need help.
We do, yeah.
yeah. Yeah. And you may
So
be the one.
so my advice, write some epsilon papers to get the next job. But then write some, think about these problems. too.
Yes. Write some Main Street papers.
Yeah. Oh, I said epsilon, you know, little,
Yeah,
little
yeah, yeah.
improvement on the last one.
Yeah. Well, that's good science and important,
Oh, yeah.
but the lottery ticket of a new idea that grabs people is very seductive.
And I see friends in the audience who've been doing that. Another question?
Hi, I'm curious to know if there was ever a time in your career where you doubted yourself, not particularly in your ability to do physics, but interested to hear your experience and maybe advice for early career researchers who are struggling to find stability in their careers.
Yes, yes. You do have to bear in mind that when I was your age, it was not long after Sputnik, the US started realizing that it wasn't supporting scientific research very well, and that the Russians were getting ahead. The notion that the Russians could do better than the Americans was a real shot in our pride. Actually, I'm Canadian, but I understand. I understand. So life was easier. I just have, in those days, you know, it was not that long after the Second World War when physics had made enormous contributions to war effort. Not only the atomic bomb, but radar, proximity fuses, lots of things. After the war, the military remained deeply impressed by what physicists could do. Big businesses also, wow, if these pointy-headed individuals can do all that during a war, what could they do? They took, you know, to inviting a prominent physicist to spend a few weeks just roaming around their operation in hopes that he'd drop a hint to what's going to come next. And in particular, I was supported in my research for a time with the Department, the Naval, U.S. Navy, Department of the U.S. Navy. What do I have to do with the U.S. Navy? Zero. But yet they were willing, the cost of supporting me dropped off the edge, you know, of significant figures in their budget. Then Senator Proxmire, was it, decided that our little psyches were being affected by association with the military. This was during the Vietnam troubles. And so he passed a law that the military could not support unrelated research. This good deed cut off a supply of research that was so important in the 50s, so valuable because you could do something wildly speculative, but good thoughts sometimes can have very bad unintended consequences. The present situation could be improved. I'm sorry, I've forgotten what your question was.
Oh, that was really interesting. I wanted to know if you had any advice.
Yeah, well, first, Katie said it well. First, submit to following the directions that your superiors, only in age, but not in true intuition, feel is a good idea. Add some decimal places to this or that measurement. That's good science. It's great experience. But of course, spend a little time thinking, as one says, outside the box. You know, I don't remember what, I tend to say things in many times because I've been saying them so long. But to add decimal places is great science, but it requires close focus on one specific direction, which is very important and will get results, but you have lost the ability to look sideways. And what in the world, why am I thinking of this rather than that? And so if you spend a little of your time thinking outside the box, and there are many questions outside the box, you just have to let your mind roll free. So my picture of a successful young scientist these days is a good track record on received ideas, but then the occasional insight that maybe is something interesting. Often the insight will be wrong, but that's all right. You're establishing a record, and maybe one of the ideas is profitable. It's not an easy path. But yeah, but the way it is.
Now, we have a good online question,
Okay.
which I will read aloud. The DAISY collaboration at Kitt Peak, Arizona presented results that suggest the effect of dark energy may be weakening over time.
Yeah.
Statistically not yet significant, but if true, what does this tell us about the nature of dark energy?
Well, of course, I can't answer that, despite the fact that, yeah, people have been looking for a long time. Is the dark energy density truly constant? If it is, it's a constant of nature, and that's just the way it is, live with it. But if the value of the dark energy density changes even a little bit, and if you can establish that reliably, you have learned that it's not a constant. That's a deep, deep advance. It's dynamical. It invites theories about how it could be changing. So it's a wonderful line of research. They're looking hard. I wish they hadn't announced it with quite such fanfare, because it's not really all that reliable. But they're continuing. They're going to keep working on this problem. And if ever we get positive evidence of a change, it will be a dramatic advance, and it will stimulate a lot of new ideas.
So I think on that note, we should give Jim a break. Thank you so much for this wonderful.
Thank you, my friends. Thank you.
Fabulous.
Oh, thank you.
So